Hi folks, we're going to take a look at page 389, number 29. So here what they are asking for is the width of this river, so that's represented by B, so going straight across at a 90-degree angle to the shore. And what they've done for us is they've created this triangle with these two angles on either side, and they've told us that the distance of this side here is 100 meters. All right. So given that the only thing we have access to is our right angle trigonometry, so using sine, cosine, and tangent within a right angle, we come to a problem right off the bat because all we have in each of these two right angle triangles, so they helped us out here by drawing that line B for us, showing us these two right angle triangles, but all we know is an angle and the fact that it's 90 degrees, not enough. You need a side length. Now you don't quite have a side length in either triangle, but you do have this 100 meters, which is the sum of these two side lengths. Okay, so the fact that we need to somehow use a variable to represent these two side lengths means we'll probably have to solve a system of equations because we've got the variable that we're looking for, b, and the way we can deal with this is by saying, well, I'm probably going to want to work with this side length, so let me give it a name. Say we call it x, and I'm likely going to want to work with this side length in the lower triangle since it makes up part of that 100 meters, but instead of calling this something like y, I can write this as 100 minus x. So I'm able to describe these two sides in the different right angle triangles using the same variable. So what I have now is I have a scenario where I'm describing the sides of a triangle using two unknowns. So that tells me I'm probably going to have to solve a system of equations. So let's try to write a system of equations with b and x so that then we can solve it. Okay, now let's start with this top triangle, and I realize that the two sides that are of interest to me are the opposite side of the angle and the adjacent side. In fact, it's the same thing for the lower triangle, the opposite side and the adjacent side. I have no information about, nor do I really care about the hypotenuses. So that's why I'm going to work with tan. Okay, so my first equation, which I'll do from the upper triangle, is we can write that tan of 85.6 is equal to opposite over adjacent, so b over x. And then we can write a second equation in the lower triangle, tan of 79.8 is equal to opposite b over adjacent, and the adjacent side is 100 minus x. And so we have a system of two equations and two unknowns. So let's see if we can solve that by either substitution or elimination. Now this is where we have to make a decision because tan of 85.6 degrees really just represents a number, just represents some ratio. Okay, but if I put this in my calculator, I'm going to get something that's got infinitely many decimal places. So it's not the nicest of numbers to work with. All right, so what we could do is make an approximation, which is perfectly fine, but it means we lose some accuracy as we go along the way. The other option is to just keep it as it is throughout the whole process and only at the very end do my approximation. So I'm going to do it both ways, but let's start by approximating this. And the way to avoid, okay, so we'll call this option A. The way to avoid losing too much accuracy is to always keep 4 decimal places when you're working with a trig ratio. Okay, so let's find tan of 85.6. So tan of 85.6 is 12.9962. So that's, so let me go here, that's 12.9962. Okay, and right off the bat, I'll start doing some algebra because I don't want this x in the denominator. So let me multiply both sides by x. So here that's times x equals b. All right, and now from the other equation, I'm going to find tan of 79.8, which is 5.5578. 5.5578. So 5.5578. And again, same thing, let me do some work while I'm at it, is I don't really want this 100 minus x in the denominator, so I'm going to multiply both sides of the equation by 100 minus x. So times 100 minus x equals b. So if I multiply this side by 100 minus x, cancels out with that one in the denominator. All right, now we have again a different view of our system of equations. Now since the b's are already isolated, I think I'm just going to do a substitution from this point here. Even though b is what I'm looking for, I think it's just easier to do the substitution, solve for x, and then go back and find b afterwards. Okay, so I'll replace this b by this expression here. So on the left-hand side, we'll have 12.9962x equals, and I know I'm going to want to distribute this, so I might as well do this right away. So I'm multiplying by 100, so it's just like moving the decimal place 2 spots. So it'll be 555.78 minus that number times x, so 5.5578x. And now this is a pretty simple linear equation to solve. So I'll bring this to the other side. I'll add it to both sides. So here, what do we have? We've got 12.9962 plus 5.5578. Okay, and that gives us 18.554. So 18.554x equals what we had left on the other side, so 555.78. And finally, I'm going to divide both sides by the coefficient to solve for x. So here we've got 555.78 divided by 18.554. And that's equal to 29.95. Approximately. All right, but of course what I'm actually looking to solve for is the b value. So now I'm going to stick this into one of my equations. I'll use the first one since it looks much easier. So we have 12.9962 times x, which now we have as 29.95, is equal to the b value that I'm looking for. So let's do that. Well, I already got it in the calculator, so I'll leave it there. So times 12.9962, and that's equal to 389.3, we'll say. Okay, so b is equal to 389.3, and I believe in the textbook they ask us to the nearest 10 meters, so I guess this will go to 390. So b is approximately equal to 390 meters, and there's my answer. Okay, and that's a perfectly valid way to solve this problem. Okay, but as we've done in class, let's see if we can solve it without having to actually do that approximation right off the bat. All right, so and this, if you learn how to do this now, it'll come in handy later on when you're solving some of these more complex equations. All right, so I'm going to do the exact same thing now. I'll call this option B. Exact same thing, except I'm going to keep this in symbolic form. So it's kind of like keeping pi in an equation as you're solving it instead of replacing it by, say, 3.14. Okay, so do the same thing with the first equation. I'll multiply x to both sides. So we have x times tan of 85.6, okay, equals b. Now notice in order to not confuse what's inside or outside of the tan, we tend to put numbers and variables in front instead of afterwards. Okay, just a bit of a convention. So I'll do the same thing here. I'll multiply this to the left-hand side, the 100 minus x. Okay, so we have tan of 79.8 times 100 minus x equaling b. And like before, since the b's are already isolated, I'll just do my substitution here. I'll substitute this b with that expression. So we have x times tan of 85.6, okay, equals, and I'll do the distribution here. So it'll be 100 times tan of 79.8, okay, and then multiply to the x minus x times tan of 79.8. All right, I'll collect all the x terms to one side of the equation, so I'll add this to the other side. So we have x tan 85.6 plus x tan of 79.8 equals, well, we still have this on the other side, 100 tan of 79.8. Now, if you notice, these are the exact same steps I followed on the left. The only difference is I'm carrying around these symbols along the way. Okay, so again, how do we add two like terms? Well, we just add the coefficients in front of them. So this is like having x times 10 of 85.6 plus 10 of 79.8 equals 110 of 79.8. And of course, lastly, we just divide this coefficient to both sides of the equation in order to isolate x. So x is given by 110/79.8 divided by this whole expression, 10 of 85.6 plus 10 of 79.8. Okay, and so now what we've managed to do is to save the whole approximation for the very end. Okay, now in fact, if we wanted to really take this further here, I don't even have to determine this value here, because in the end, what I'm looking for is b. All right, so I can use this first equation and replace x by this whole expression here. So in fact, that's what I'll do. That'll even save, give us even more accuracy. So what I'm looking for is b, which is equal to x, which is this whole thing, 110 of 79.8 over 10 of 85.6 plus 10 of 79.8, okay, times 10 of 85.6. All right, and let's now find our approximation for b. Okay, let's see what we got here. And again, we have to be very careful about how we input this into the calculator. Now, first of all, this is like that number over 1, so I could just multiply that out to the numerator. So let me do the whole numerator, 100 times 10 of 79.8, close bracket, times 10 of 85.6. Okay, and there we go. And let's divide that now by the denominator here and make sure you open up a bracket. Okay, because if you don't, it'll just divide and then add that answer to the other expression. So you have to help this calculator out with the bedmess of it. Okay, so here we have 10 of 85.6, okay, plus 10 of 79.8, and there it goes. Hey, pretty much the same answers we got before, 389.3, and of course, since they want it to the closest tens, we have 390 meters. Okay, so as you can see, we didn't really lose much precision doing it with these approximations, and that's because we kept the 4 decimal places. If you don't keep the 4, 3, you only keep 3 or 2, you start to lose some precision. All right, so let's do a quick recap. Number 1, how do these types of questions work? Okay, when you see that you've got a couple of right angle triangles, but neither of them individually have enough information to solve the problem, that should give you an indication that you're going to need a system of equations. In this case here, it was about noticing that the sum of these two sides was equal to the given value. Some other questions, it might be the difference that's given between two important side lengths. Okay, from there we use tangent to set up our system of equations, and then we had our 2 alternate ways for solving this system. One by doing our approximations at the very beginning, and the other by keeping our approximation till the very end. But we got pretty much almost identical answers, so either of them works perfectly well. Okay, that's it for this one.